Okay. Good evening, everybody, and welcome to the January lecture meeting of the Royal Astronomical Society of Canada, Toronto Centre. I'm the President, Ralph Chu, and tonight we have a lecture that I will introduce our speaker in just a moment. Is there anybody here for the first time? Quite a few, great. Welcome. This is one of two types of meetings that we have throughout the year. Tonight we will have a formal presentation. Our other kind of meeting I will talk about later on when I announce the events for the next 4 weeks and tell you all about those things later on. Let's get right into our talk by introducing our speaker, who really doesn't need a great deal of introduction, but we were just talking outside before the meeting started, and it's now the 4th January in a row that our speaker has filled in the gap for January. Paul Delaney is a familiar face to the Canadian public. He is the face of astronomy to the public in many ways. Since joining York University's Department of Physics and Astronomy in 1986, he has become a frequent television commentator on astronomical events. Now a university professor and director of the Allan Carswell Astronomical Observatory at York, Paul is a dedicated, enthusiastic astronomy educator. He has been a member of the RASC since 1980 and served as our second vice president since 2009. He is the recipient of the 2010 Sanford Fleming Medal of the Royal Canadian Institute, the 2015 Keelock Award of the Canadian Astronomical Society, and the 2017 Klumpke Roberts Award of the Astronomical Society of the Pacific in recognition of his work in astronomical outreach. Tonight, Paul is going to be speaking on exoplanets. Please welcome him.
On here, yes I am, very good, okay, like that. So, exoplanets seems to be one of the really hot topics in astronomy, and actually I don't even have to stand here because I've got this remote control and I'll drive Andrew and company nuts by walking around. Exoplanets, even as I was sort of going through my presentation this afternoon, making sure that the I's were dotted and the T's were crossed, what would pop across my desk, but two new habitable zone exoplanets that were found, and they were far enough out that they weren't being tidally locked, and so exoplanets seem to pop up on such a regular basis. And you know, we've had certainly a number of presentations here over the years keeping you up to date on the latest exploits of observatories around the world and above the world, keeping us fully informed on planets around other stars. TESS, the Transiting Exoplanet Surveying Satellite, is in fact the current, arguably premier instrument that is adding to the rich repository of data left behind by Kepler. But more of that in just a moment. So, the usual ad, okay, the university likes me to mention where I'm coming from. The Allan Carswell Observatory on the main York University campus. If you're at all interested in dropping by on a Wednesday night, when we're not meeting here, by all means, at this time of the year, 7:30 to 9:30, you get a 1 hour slot, 7:30 to 8:30, 8:30 to 9:30. It is a ticketed affair. It's not charged. It's free, but with the 1 meter telescope that's there, which is a really nice telescope, there's a lot of interest and a lot of demand. So we now ask you to register so that groups of 25 can go through and have a really good time for an hour looking through the telescope with my students. So throughout the year, by all means, please drop in and have a look through the telescope. We've just actually ordered a neutral density filter so that we can actually look at the moon. It was giving us moon blindness. It was really, really bright with a 1 meter telescope. Here's the 1 meter up in the top left, and I'm guessing that there is a pointer in the middle. There we go. Okay, so here's our 1 meter telescope. Really wonderful instrument. It allows us to scoot around the night sky very, very quickly, reaching limiting magnitudes that we just have not been able to see before. So it's a really nice instrument to come and visit. Okay, enough of the ad. exoplanets, planets around other stars. If we were having this conversation, roughly speaking, 30 years ago, the number of planets that were known to exist in our galaxy anywhere was, well, at that point in time it was 9. But of course, as we know, Pluto ran into a little bit of trouble there in the early 21st century. But all of the planets that we knew about orbiting around a star, any star, were all in our own solar system. Now that began to change in the early 1990s, and as you will soon see, and as you probably know, there are now thousands and thousands of exoplanets, to the point where we are quite convinced that every single star in the Milky Way galaxy, and therefore by inference probably the galaxies beyond, possess planetary systems. So it is an area of astronomy that has really become huge over the last 25 years. And when you sort of run your finger down the astronomical faculty and the projects that are being mounted at almost any university, you see exoplanetary discussions and exoplanetary observations. And there are satellites being built almost continuously now to place assets in orbit where we'll be able to look for more and more exoplanets. Okay, how do you find an exoplanet? It's actually surprisingly easy. It's sufficiently easy that you begin to scratch your head and think, why weren't we doing this decades ago, not just over the last 20 to 30 years? But hindsight 2020. There are a number of different techniques, far too many for me to go through tonight, but let me just lead you through the top 3. We're able to find exoplanets by direct observation, although that's a little on the tough side and it's a bit of a specialized observation, but nonetheless we can detect exoplanets directly, visually. We are also, of course, able to measure the presence of exoplanets courtesy of their influence on their parent star, so measuring radial velocity or utilizing the Doppler effect or the wobble effect. It goes by a number of different names. And then, of course, there is arguably the most successful detection method to date, and that is the transiting technique, where we are looking at a slight drop in light as a result of a planet passing in front of its parent star. Very much like, for example, the transit of Mercury that none of us saw in November. Okay, so direct imaging. As the name suggests, we're actually able to detect the presence of planetary light. Now, remember, planets are not self-luminous objects. They only shine by reflected light. They are dirty mirrors. And so being able to detect directly that planetary reflected light is really hard, because those planets, generally speaking, are relatively close to their parent stars, and the star is very, very bright. The planet is relatively faint, and therefore direct imaging of a faint light right next to a bright source of light, very, very tough, especially at the bottom of an atmosphere where there's a great deal of scattered light in our atmosphere, and it's just tough. But it's not impossible, especially if you occult the parent star, and that's what you're seeing here. We're actually having a little bit of a disk in front of the starlight, and that allows the telescope and its instrumentation to be sensitive enough to see the fainter light of the planets, 3 of them in this particular instance, that are moving around the star. Now, this is an animated GIF. It spans about 7 years of data observation from the Canada-France-Hawaii telescope. So it takes a long time with imaging to be convinced, yes, that really is a planet that is in a bound orbit around its parent star. But nonetheless, we can do it, and there are some really neat instruments that have now been generated and are on 3.5, 4 meter class telescopes down in South America, in Chile, that are actually more directly searching the inner space near stars. You recall most of the observatories down there in South America are up high above a lot of our atmosphere, whereby we're able to look through much steadier air. And when you're talking about multi-meter class telescopes with great sensitivity, CCD systems and so on, then you're improving your chances of being able to detect directly exoplanets. So you're going to hear more and more in the coming years about direct observations, and we're actually now to the point where some of those nearer exoplanets are being observed, and we can actually generate weather forecasts on those exoplanets. We're looking at the cloud cover and the way it changes in those planetary atmospheres. So direct imaging, while it is tough to find planets that way. It's certainly not impossible, and once we have found them, our telescopic assets are being turned more and more towards these direct observations. The Doppler effect. Well, everybody in this room probably is aware of what the Doppler effect is. It is associated with any wave-like phenomena, so sound waves as well as light waves. Most of us have experienced the Doppler effect associated with sound. You're sitting at a railway crossing or you're sitting at a traffic light and you hear a distant siren of some description or a horn that is approaching you, and as it approaches and comes level with you and passes by, you detect a change in pitch associated with that particular sound. Not the intensity. Obviously the intensity is changing as well as the distance to that source of radiation, that source of waves is changing, but it is the pitch. As it's coming towards you, it's at a slightly higher frequency, and as it's receding away from you, it is at a slightly lower frequency. As I say, we can hear that with sound quite easily. It also applies to light. So basically the Doppler effect is the apparent change in the frequency or the wavelength of the wave, sound or light, that you're hearing as a result of relative motion between the source of the radiation and the receiver, you in this particular instance. That sounds a bit of a mouthful, so pictures are worth 1,000 words. If we're looking at a distant star system, we can see the star. If the star is perfectly stationary, we can take the starlight, pass it through a spectrograph, and break it up into its component light waves. And we can see composition, temperature, all sorts of really nifty stuff associated with that star. But the important point here is that if the star is stationary, the spectral lines, the signature of that particular object, are stationary from our perspective. If that star begins to move towards or away from us, towards us, blue shifted, red shifted, if it's moving away, then those same spectral lines, highly exaggerate, begin to sort of sway backwards and forwards in the spectrum. Now, it's only a fraction of a nanometer that it's moving, but nonetheless, we can detect that to and fro motion as a result of the star's motion. What's causing the star's motion? Enter exoplanets. The exoplanet and the star are actually moving around their common center of mass. It's easy to think that an exoplanet is just moving around the center of the star, but it's not. They've got combined mass. Draw a line between the centers of those combined masses, and at a point which is admittedly quite close to the center of the star, there will be a center of mass about which both the planet and the star are moving. Let's try this again here. Okay, so here you've got the star, highly exaggerated here, obviously, just to make the point, and you've got the planet. So the planet is moving around in its orbit around the center of mass. So too is the star moving around that center of mass. So draw a line like a dumbbell rod between the star and the planet, and now you are actually able to sort of see the motion that the planet is engaged in and how it's influencing the parent star. As a consequence, the star, as the planet moves in this direction, the star moves in this direction. From our point of view, the star is coming towards us just a little bit. And then, of course, as the planet, down here, moves further around here, so too is the star now moving around in this direction, moving away from us. Depending upon the orbital period of the planet, so too will the star do this to and fro, this wobbling motion, which we can detect using the Doppler effect. And so by measuring how far these lines move, how much of a change there is in the frequency or the wavelength, then we can infer the mass of the planet that is actually doing the perturbing of this particular star. Very, very powerful technique. This was actually first pioneered all the way back in the 70s by two Canadian astronomers, Bruce Campbell and Gordon Walker, out from the West Coast, UBC and UVic. Bruce Campbell was one of the observers, I've forgotten the exact term, but one of the support astronomers at the Canada-France-Hawaii telescope. And so he had a bit of discretionary time available to him. And so he and Gordon Walker devised the radio velocity detection technique, whereby they would look at the motion of a selected group of stars with the view of watching this motion and inferring the existence of planets. So please note, we're actually observing the star, not the planet, but the planet is causing the star's motion. So they utilized the Canada-France-Hawaii telescope. They got a really nice data set using this technique, and they analyzed it. They published their results in 1988. They were not convinced from the data set that they had picked up that they were able to see evidence for exoplanets. They were suspicious. They were very confident in the technique that they were utilizing, and so they should have been, but the data just didn't suggest categorically that there were exoplanets present. And the simple answer to what was the problem is they were ahead of their time. The sensitivity of their equipment just wasn't quite up to detecting the types of speeds, the motion, that the stars were exhibiting. This was, remember, late 70s, early 80s. As it works out, the 16 stars that they were actually observing, at least 3 of them have now had confirmed exoplanets orbiting around them. So they had the right data set, or at least they had members in that data set that have got exoplanets, but their ability, their sensitivity to detect the motion just wasn't there. It's unfortunate because, of course, this was in the mid-80s. It wasn't many years later that the first detected exoplanet orbiting around a sun-like star. There was pulsar detections a few years prior to this, but in 1994, Mayor and Quilo, utilizing exactly the same technique that Campbell and Walker had pioneered, but with 10 years better technology available to them, made the detection. 51 Pegasus B, lowercase b, that always represents the first exoplanet found orbiting a star, and then lowercase c for the second and lowercase d for the third, and so on. Quilo and Mayor found 51 Pegasus B and published their results in October of 1995. You might recall last year they helped share in the Nobel Prize in Physics for this observation. So some 20 years later, they were heralded for their efforts in this regard. The first exoplanet that we did find orbiting this sun-like star, you can see here that it was a fairly massive object, half the mass of Jupiter, but look at the stats with respect to its orbital configuration. Orbits the parent star every 4.2 days. Remember, Mercury in our planetary system takes about 88 days to spin once around the sun. This one orbits with an orbital period of 4.2 days. Very, very close in, 5/100ths of an astronomical unit, where an astronomical unit is the distance from the Earth to the sun. So this is what we call a hot Jupiter. Very tight orbit, very massive object. That's the best way to find, the best conditions to be able to find exoplanets. Big mass and relatively small diameters. As I said at the beginning, fast forward, based upon the data that we've been collecting over the last 25 years, we can now say with statistical confidence that every single star in the Milky Way galaxy has a planetary system. We can't tell you how many planets are around it because those numbers vary at the moment. We've got lots and lots of stars where we've found just one exoplanet, but there are many examples where we've found up to 8 planets in orbit around their parent stars. Okay, the third technique that I want to draw to your attention is the transit technique. As I said earlier, this is where, from our perspective here on Earth, we watch a planet, an exoplanet, slide in front of its parent star. And of course, if you're looking at the star without the planet in front, it shines, and we have a baseline of intensity that we are able to measure. And then if the exoplanet begins to slide across in front of it, regardless of the size of the exoplanet, it's going to block a little bit of light. And so if you're very careful doing photometric observations, you can detect that really subtle dip in light. It's generally speaking about 1 to 2%. The largest one I think I've seen is about 3.5%, and they can be much less than 1%. But ballpark figure, 1 to 2% of the light will be blocked as the exoplanet slides in front of the star from our perspective. Now, obviously, not every star has to have its planetary orbits in our line of sight. Mercury and Venus, as we know, are able to transit our sun from our perspective here, but not every year, not every month. Sometimes, as in the case of Venus, we get it twice a century or thereabouts. Okay? So you've got to hang in there for a little bit of math. Nothing says that it has to be on a particularly regular basis. If, of course, the planetary system from our point of view is orbiting around its parent star sort of in this plane, we'll never see any transits. So you've got to wait for that plane of the planetary system to become edge-on effectively from our point of view. So not every star is going to give you the opportunity to see a transiting planet. But a certain fraction of them, yes. So this is the type of light signature we are looking for when an exoplanet slides in front of its parent star. Now, depending upon how big the star is, depending on how big the planet is, depending on how far away, all those variables come into play to tell you how long this dip in the light curve will last. If it's very short, that tends to suggest that the planet is in a very tight orbit. If it's a little larger, it tends to suggest to you that the planet is a little further out. Bottom line to it is that there is a rich amount of data that is available from that light curve that all gives us insight into the characteristics, the radius, the orbital speed, and so on, of that exoplanet. That type of photometric observation actually is child's play. Measuring a 1% dip in light is something that our third year class at the university not only does, has to do for their project. That is their project. And we're next week actually starting a graduate course that has got to do this as well. So it's relatively easy to make these observations now, given modern technology, CCD technology, and so on. So transiting exoplanets, fairly easy for all sorts of observatories to be able to utilize. Okay, so those are the three techniques that I just wanted to alert you to. How have we taken advantage of these techniques? Well, we've all heard of the Kepler Satellite. It was launched in 2009. It operated for 9 years or so. It stopped operating in 2018 in two different modes. For 4 years, from 2009 to 2013, it basically was staring fixedly at one area in the plane of the Milky Way galaxy. It was an area between Cygnus and Lyra, and it was looking at, give or take a bit, 200,000 stars continuously, like 4 years, every minute of every day for 4 years. It was monitoring these stars, looking for the changes associated with starlight, so looking for these light curves. It was a relatively modest-sized telescope, but it was a telescope that was doing this. And then after the attitude control wheels that kept the telescope pointing, you need 3 to stabilize telescope and be able to point it accurately. When we fell down to 2, they rejigged the way the mission was going to operate, and they were fairly crafty, and they managed to figure out a way to use the two remaining reaction control wheels and the solar wind to actually stabilize the spacecraft, but we were no longer able to look at this patch of sky in the Cygnus-Lyra area. But we were able to continue for 4 more years worth of data. An incredibly successful mission, and about 2/3 of all of the exoplanets and exoplanetary candidates that we are aware of today are arising from the data observations of Kepler. So we're still busily going through all of this data, even though the mission itself has finished. Okay, this gives you an idea of how good we've gotten at finding exoplanets. So down here, okay, as you can see, not much action happening. Here's 51 Peg, okay, and then things began to get better and better and better. So the red represents planets that are a little close in, a little toasty, shall we say, with respect to habitability criteria. The green represents just right, the Goldilocks zone. The planets in question are in that region of their solar systems. And then the blue represents a little further out. Now you might look at this and go, well, my gosh, most of the planets anywhere happen to be a little bit too close to the sun. How can that be when you look at the planets in our solar system? Remember, this is a bit of a selection effect. It is easier to find exoplanets which are in tight orbits around their parent stars than finding planets that are further out. If you are watching planets go through the transit effect, then as they're orbiting around their parent stars on timescales of days, tens of days, perhaps hundreds of days, you can see multiple transits in a fairly short period of time. If you've got a planet that's going around its parent star in 20 days, obviously every 100 days you'll detect 5 transiting light curves. That gives you great confidence that the object that you're looking at is in fact an exoplanet. But if you're looking for a planet, say a Jupiter distant object around a parent star, where its orbital period is 12 years, now you've got to wait, it's passed in front, go off and do 2 or 3 more degrees, come back, there it is again, and you want to see it at least 3 times to be able to be sure that it really is a transiting exoplanet. So the further out the planets are from their parent stars, and therefore green and blue designations, the longer the time frame is that you need to make those observations. So this graph is deliberately selective. It is biased, if you will, to the types of observations that we are making at the moment. So it doesn't suggest that exoplanets only hang out close to their primary stars. But as you can see, we've got lots and lots of success as time has gone by, and it's only getting faster and faster because we're getting better and better at this process. Okay, I'm always asked, how many exoplanets do we have? So I looked it up, January 2. I've actually got this slide for the 10 years or 15 years that I've been giving this type of presentation. I can still remember so excitedly that we went from single digits to double digit exoplanetary finds. When I put in 12 exoplanets to now know, I was really quite excited about the whole affair. Now it's a real pain because, of course, it's thousands and thousands, and the definition of an exoplanet, just like the definition of a planet, is a little bit debatable. And if you look up 2 differing exoplanetary catalogs, they'll be different. Anyway, so like any good researcher, exoplanet.eu is where I consistently look up the number, and let's cut to the chase. 6,677 and counting planets or planetary candidates are now known to exist. Of that, 4,000 and change are confirmed exoplanets, and the prevailing wisdom is that all of those exoplanetary candidates that are there, somewhere over 2,000, 2,500, 90 to 95% of them will be verified. It just takes a long time for us to verify the observations, because once a candidate is found, you need to observe that with a different instrument, preferably a different group, and generally speaking, the best follow-up observation is a radial velocity using the Doppler effect. A lot of these stars are relatively faint, so we can't do it at a university. You need a big telescope time, and big telescope time is in short demand. Generally speaking, most big telescopes around the world are oversubscribed by factors of 3, 4, or 5. That is to say, for every single clear night that an observation is made, 3 or 4 more could have been made on that same night. So there is fierce competition, which means fairly limited amount of follow-up time is available to confirm these exoplanetary candidates. At any rate, probably if I'm doing this again next year for you, it'll be about 7,000, so we'll have another milestone. What is perhaps most interesting about that collection of exoplanets that we have found is the distribution of mass. Now, when we started out back in 95, we kept finding these hot Jupiters, and everybody sort of thought, oh gosh, why is it that the only planets we're finding outside our own solar system are really big and massive and Jupiter-sized and larger, and they're all in really tight orbits around their parent stars, and they're all very, very hot? What's wrong with us? Why are we so different? Well, of course, as time went on, that selection effect began to subside. I mean, it's not that dissimilar to if you were ET and you came down to visit Earth, and the first thing you did is you went and visited a Raptors game. You'd look at all the people on the court and go, gosh, they're huge, okay? It's a selection effect. So we've now got enough data out there, nearly 7,000, to say the distribution of the planetary mass is in fact more even, more regular, along the lines of what we would expect. So you've got a small tail associated with the massive planets. Here we are down at the Earth and super-Earth end. There's a good number of it. But by far the majority of the planets in terms of mass are in the Neptune-Uranus type size scale. In fact, there is a collection here of super-Earths, which we actually don't have in our solar system. Mercury, Venus, Earth, and Mars are all sort of terrestrial planets, and we don't have anything between there and Neptune. Neptune here, okay, quite common out there. So the mass distribution is now much more in keeping with what we would have expected when we started this process out, and that selection effect of large hot Jupiters has shrunk back to a more normal scale. Don't have time to talk too much about it, but down here, in fact, this super-Earth area, we're beginning to collect enough statistics that suggest that there is two distinct areas of mass associated with super-Earths that are just a little bit over the mass of the Earth, and then about 3 to 4 times the mass of the Earth. There seems to be a little bit of a lack of exoplanetary sized masses that are in and around 2 times the mass of the Earth. And so people are beginning to look very carefully at these statistics. We're now beginning to generate enough exoplanetary finds to be able to look at this mass distribution of exoplanets. And it does look as if there is a little bit of a gap between just around the mass of the Earth and about 3 to 4 times the mass of the Earth. Not shown on this diagram, but it looks to be a real effect. If you take all of those exoplanets that we have found, so this is not the candidates, this is the 4,000-ish exoplanets that we have really detected, and you plot their orbital period, so basically how far they are away from their parent stars, against their actual mass, so here you see the guys in our solar system, so to speak, you can see that there is a fairly significant amount that are close into their parent stars. This is a logarithmic scale. Just be careful of that. 1, 10, 100, 1,000. Okay. Still, we're seeing the vast majority of exoplanets that we're detecting close in. Okay. But there is quite the range of distances, okay, that we're detecting, and quite the range of planetary masses. So and you'll notice there is this fairly sharp cutoff here at about 1 to 2 years. And that's what I was referring to before. If you're watching an exoplanet and it's got an orbital period of 2 years, you need to be observing it for 4 to 6 years to be certain that you found the exoplanet. We've not got a very long base of operation for patrol survey exoplanetary telescopes at the moment to be able to push outwards in this direction as far as orbital period is concerned. It's coming, but it's slow. It's much easier to find the planets that are sort of 10 to 100 day orbital period. Anyway, the takeaway message here is that we do have quite the distribution of mass and a good healthy population of planets that are in orbits relatively close to their parent stars, which means the notion of the habitable zone is one we need to discuss. So the habitable zone, generally speaking, is that region from the parent star at which the planetary surface temperature will reside between 0 and 100 degrees Celsius, which means, of course, the possibility of liquid water is existing on those planets. Now, there's all sorts of additional criteria. is there an atmosphere? Because obviously if there is no atmosphere, you're not going to get water there. You've got the atmosphere. That's great. Is there water vapor in the atmosphere? If there isn't water vapor, you don't get water, and so on. So you have to be careful, but at least we're now realizing that there is a significant amount of real estate, exoplanets, that are residing in this region around their parent stars. And so here you've got, Mars, Earth in the habitable zone. Yes, Mars is on the outer edge of the habitable zone. It's a little chilly, but it is actually there. And if Mars had a decent enough atmosphere, which it did in the past, liquid water would exist on the surface. So this is the traditional habitable zone. If you want to get a little bit more generous, and you can slide in here and let the surface temperature rise. Okay, maybe a bit uncomfortable for you and me, but there is ample evidence of life on this planet, extremophiles, which are quite happy with higher temperatures. So the habitable zone, the definition thereof, is changing with time. But this gives you the sense of differing star temperatures and the distances from those stars at which the habitable zone where liquid water could exist on a planetary surface resides. Okay, so down here is the M dwarf stars, okay, the red stars. This is, of course, around about us here, okay, but then there are many stars that are much brighter and therefore higher surface temperatures. And the higher the surface temperature, the further out you will go as far as the habitable zone distances are concerned. Okay, so this is the traditional thinking for looking for signs of life on planets that obviously have got some water associated with them. But in the last decade or so, there has been a bit of a change of thinking, and that is associated with the water worlds that we are finding and the exomoon water environment. Think of Europa. Think of Enceladus. There is a surprising amount of water in our solar system in regions which are well and truly outside of the habitable zone. And so, yes, this is the traditional thinking for the habitable zone based upon temperature and therefore distant from the parent star, but we are now exploring the idea that life could well establish itself on other areas in the solar systems or in those planetary systems that are not within the habitable zone. So stay tuned in that regard. Okay, so where are things at the moment? Well, on the surface of the Earth, we're certainly looking hard for exoplanets. There are many, many patrol instruments out there that are monitoring stars, looking for these telltale signals, either the transiting signal or in fact the radial velocity, the Doppler wobble. But the latest asset is TESS, the Transiting Exoplanetary Survey Satellite. I draw your attention to these four shrouds that are in here. Okay, so this is basically one big baffle to keep stray light from the Earth, the Moon, the Sun out of the optical system. But these four baffles here are basically protecting very large telephoto lenses. So there aren't any telescopes on TESS. It's rather CCDs at the bottom end of these long telephoto lenses. So TESS was launched in 2018, so it's been operating for a year and a half. Well, I guess it's coming up on 2 years in April of this year, although its science mission didn't start until June, so it's a year and a half in. Unlike Kepler, TESS is a full sky survey instrument. Remember I said Kepler, for its primary mission, was fixed on an area of sky. It was about 100 square degrees, but it was one particular area in the Cygnus Lyra area, and it didn't deviate from there. The Kepler 2, the K2 mission, did grab some different patches along the ecliptic, but you could never think of Kepler as an all-sky instrument. TESS, however, is designed quite differently. Its plan is to image about 85% of the entire celestial sphere, so every corner of the globe, but instead of using a telescope with a large collecting area, they're using essentially telephoto lenses. These are very fast systems so that they can pick up big swaths of sky. In fact, every time TESS takes a data set, it's about 24 degrees wide and about 96 degrees long. between these four systems. The plan is to image bright stars, the 200,000 or so bright stars that are, quote, relatively close to us, within a few hundred light years. The plan for these bright stars is, once we've found exoplanetary candidates, is to ship all of that data down to observatories around the world for quick follow-up observations. And if you're looking at bright stars, you don't have to necessarily use big telescopes. And remember, I said telescope time is really precious. So now you're bringing the data down, and all you have to do is look at, say, a 10th or a 12th magnitude star rather than a 16th or a 17th. And now telescopes, even like those at York University, are able to do that. So follow-up observations are planned around the globe far faster for the TESS candidates than we were able to do with the Kepler telescope. And of course, bright stars will also allow telescopes like the James Webb, assuming it launches in 2 years, to be able to look at those planets and image them in their full glory. So TESS has a very different agenda to Kepler, even though they're utilizing the transit technique to again make measurements and detections for these exoplanets. So most of the stars, as I said, are going to be within a few hundred light years. TESS is in orbit around the Earth. It's an interesting orbit, about 13.7 day orbit. Goes out almost as far as the Moon. When it's way out there, of course, it's moving relatively slowly, takes lots and lots of its data. And then when it swings back close to the Earth, sort of like halfway through its orbit, it then transmits its data back to Earth at high data rates. So it goes out, makes some observations, swings back, squirts all the data at us, and then goes on out again. So a different type of orbit. Okay, the plan is for it to orbit for about 2 years. It's running perfectly, so you can bet that that mission extension is going to take place. Here you can see the differing CCD images. This is first light for TESS that took place around about June of 2018. And so you can see here, this is one of those telephoto lenses with the 4 CCDs, second lens, third lens, fourth lens, and that gives you your 24 degree by 96 degree strip of the night sky that TESS is using strip by strip to build up a picture of first the southern celestial sphere and now currently working its way through the north celestial sphere. I think I actually have okay. So here is these swaths. They observe for about a month, and then they move on and work their way around the entire hemisphere. And they did that for the southern hemisphere. It took about a year, and now they're working their way through the northern hemisphere. Let me just back up here. So this gives you the various stats associated with the optical system. As you can see, it's very, very fast, 1.4 type system. 4 CCDs here, 4,096 square. So there's a lot of data that is coming through, and it's, of course, in the visual part of the electromagnetic spectrum. So, as I say, TESS had a very different agenda to Kepler, but at this point in time, it's proving its worth. It's found somewhere in the vicinity of 150, I think it is, 1,400 planetary candidates, and 34 have been follow-up detections to confirm what they have found. So these are the types of observations which are coming thick and fast. As I said this afternoon while I was looking through this, another TESS find, actually a couple of TESS finds had come through. So the data process is now really flowing very, very well. You can expect just about daily announcements from TESS over the coming months and years. And of course, interestingly enough, for every single exoplanet that TESS finds, that data gets shipped over to the Breakthrough Listen project, and so they turn radio telescopes, the Allan array and so on in California, onto those star systems to listen in to see whether or not ET is trying to phone home. At this point in time, to the best of my knowledge, nobody has picked up. So it is a collaborative effort there. So TESS is doing very, very well. When you look back over the last 12 months, there are a number of things that have come out, and so This just happened to be the few that I grabbed a hold of. Teagarden star, red dwarf stars, these are the relatively cool stars about which planets orbit on time scales of sort of, a few days to a few tens of days. So we really like red dwarfs because they give us transits on a very, very regular basis. In this particular instance, we've got 2 Earth-sized planets orbiting within the habitable zone of that particular red dwarf. Now, red dwarfs do have some other problems. They tend to be a little less stable than stars like our own sun. They're prone to outbursts of intense X-ray radiation, ultraviolet flares. None of that's very good for one's health. So whether or not these exoplanets around these red dwarfs really are habitable is a bit debatable. They are always in tight orbits around their parent stars, which means there's going to be a degree of tidal locking. Just look at the moon to appreciate what tidal locking is all about. Will that be good for for the development of life and so on? So just because we're finding lots of exoplanets around red dwarfs doesn't necessarily mean it's a good thing. More real estate, yes. Maybe life will be very, very hardy on these worlds, and we will go ahead and detect it at some point. But to find 2 Earth-sized planets in the habitable zone, relatively rare. I love the numbering systems here, LTT 1445AB. Okay, this is a trinary system. For the longest time, we didn't think exoplanets would be able to exhibit stable orbits around multiple star systems. Obviously, an exoplanet orbiting around a star, easy peasy, no problem. Binary stars, we've thought that the ability to retain a stable planetary orbit would be severely compromised by, obviously, the competing gravitational fields of those 2 stars. We've now found many examples of binary star systems with stable planetary orbits. Sometimes the orbit of the planet is around one star when the 2 stars are sufficiently far apart, and on other occasions the planet orbits both the stars when the 2 stars are very close together. So depending upon the criteria of the stars, you can in fact generate stable planetary orbits. We haven't found very many in the trinary department, yet this system has one. Now, it's in a tight orbit about them, and as you can see, probably a touch uncomfortable on the surface, 160 degrees Celsius, but nonetheless, it appears that the planetary orbit is, at least for the amount of observations we've made, stable. Is it stable over timescales of billions of years? Don't know. But nonetheless, we've found that. WASP 121b, this is even toastier, shall we say, and you'll notice, by the way, that these stars are relatively nearby, relatively so as to speak. This one in particular, though, has a distinctly elongated shape. I mean, it is so close to its parent star that the star is actually siphoning off the atmosphere, and we can see the gas stream from the planet being sucked towards the parent star. Definitely not a destination that I would like to visit, but nonetheless, it is an unusual planetary system. And then last but by no means least, BD 2307, we've detected a phenomenal amount of warm dust in and around this particular star. And the interpretation at the moment, to be verified, but we're fairly confident, is that one way to create that amount of warm dust, and we've been observing it for over 10 years now, is to have a planetary collision. If you have 2 sort of planet-sized objects that literally come together, then you're going to smear a significant amount of dusty, rocky material around your parent star. And we're detecting this heat excess from this planetary, from the star system, which we are interpreting to be as a result of planetary disintegration. All these types of observations give us insight into what is happening around other planetary systems, around other star systems inside the Milky Way galaxy. For the longest time, we only knew about our own solar system, and with our own entourage of 8 or 9 planets with the asteroids, the comets, and so on. When you have a sample of one, it's really dangerous to go ahead and make wide-ranging predictions with respect to planetary formation, stellar formation, and so on. Over the last 25 years, finding now 6,500 planets, exoplanetary candidates, we're learning a lot about planetary formation. And we're certainly modifying the nebula theory that was the prevailing theory associated with solar system formation. There's lots to be learned about our solar systems, all exoplanetary solar systems, by analyzing as deeply as we possibly can, as many candidates as we possibly can, exoplanets and their parent stars. There was a paper that came out just a couple of weeks ago. Water is the key element, molecule, with respect to searching for life. So these researchers took a sample of about, I think it was 19 exoplanets, and they looked for the signs of water vapor, at least, in their planetary atmospheres. And as you can see, 15 of those 19 exoplanets had detectable traces of water. What was interesting, though, is, okay, we're definitely finding water. Can't tell whether or not it's in a liquid form, can't tell whether it's in a purely vapor form. We're just detecting the signature in their atmospheres. But the amount of water that we found there wasn't nearly as much as we thought. They were relatively dry, as strange as that might say. Part of the problem here is that even our own gas giants in the outer solar system, Jupiter, Saturn, Uranus, and Neptune, we actually don't know what the water content is of those planets. And they're right in our own backyard. And part of that problem is because they're cold. And water vapor tends to condense out and is probably trapped, frozen within the interior of the planet. And when we're observing those gas giants, all we're doing is, of course, seeing their gaseous envelopes, primarily hydrogen, helium, methane, ammonia, and so on. We're not seeing much in the way of water vapor. But that doesn't mean that there isn't a lot of water vapor trapped beneath those thick atmospheres. So we've not got much of a handle, even with Juno orbiting around Jupiter at the moment, as to how much water is associated with those particular planets. So we're looking at exoplanets to help better understand the water environment in our own outer solar system. So lots and lots of work being done now looking at exoplanetary atmospheric environments. Personally, I think that is really neat. 25 years ago, we were counting 1, 2, 3 exoplanets. Now we're looking at their planetary atmospheres, and as I said, just about in a position to be able to give you weather reports of those particular planets. So stay tuned with TESS and all the other assets on our planet. We are going to be in for a really exciting period over the next decade or so as we truly explore the boundaries associated with exoplanets. Thank you. Okay.
Is there a quick explanation as to how they are measuring the atmospheres of these planets?
I don't think it is, but I'll repeat it. So is there a quickie way of describing how we're detecting the atmospheres around these other planets, the components? Generally speaking, there are a couple of different techniques. Hubble has been very good at doing this. If the planet passes in front of their parent star, the light is passing through that planetary atmosphere, and if we're careful, we can actually then detect what the spectrum is of the star without the planet there, and then the spectrum of the planet of the star with the planet there. You do a subtraction, and what is left behind is what is in the planetary atmosphere. And so in that way, we're looking at light passing through the atmosphere and making a determination of the composition of the atmosphere. That's the easiest way, if I can use that term, because you can use orbital assets very easily, directly measuring a planet's atmosphere. If you think back to that first image that I showed you of direct imaging of the planets, there's just not enough light for us to work with there. So you've got to find another light source, and the easiest one is the parent star shining through the atmosphere. So that's the primary way that we're doing these observations. I'll let the guys with the microphones wander by.
The two Canadians who developed the radial velocity method, why did they not follow up on their method with improved technology?
I'm being recorded at the moment, so over a beer we can talk a little bit more about that, but the short answer, without getting me into too much difficulty, is their funding got pulled. Yeah, and Bruce Campbell then became a realtor in Victoria. So over a beer I'll talk about that a little more. Sorry. It was unfortunate, shall we say. They did the pioneering work, but the funding to carry on did not follow up. In the 1980s, around the world, the notion of finding exoplanets was low down on most people's priority lists. They really didn't think we had the technology to do it. And the groups that were working on it were almost outliers, so to speak. And so finding funding was tough. These instruments, they're not inexpensive. I mean, they were Campbell and Walker were using a hydrogen fluoride cell to actually use as a calibrating mechanism. Now, I don't know whether or not you've used hydrogen fluoride. Probably not. It is really dangerous stuff. When Quayle and Mayor used their system, it was hydrogen iodide, much easier to work with, and so on. And all the work done by Marcy and Butler and so on, same sort of thing. But back in the 80s, hydrogen fluoride was the primary cell that was being utilized, very expensive, and as I say, it was hard to come by funding.
What will be the impact of the Webb Space Telescope when it gets going on the search for exoplanets?
It probably will have no impact on the search, but it will have a terrific impact on follow-up observations. Webb, I don't expect, is going to be utilized in any significant way to search for exoplanets. The telescope time is going to be incredibly hard fought for, and they will be certainly turning their attention, as far as exoplanets are concerned, onto interesting targets. So TESS's targets, Kepler's targets, the best targets, which basically means relatively nearby and relatively interesting in the habitable zone with big atmospheres, those planets will have Webb follow-up observations done with them. So it won't be searching for exoplanets, but we're hoping that Webb, with its 6-meter diameter, really great optics there in the infrared, is going to be able to give us, excellent images of these exoplanets. And, fingers crossed that that actually happens much sooner than later.
Brian, we'll get you first and then
The triple star system, which is shown over there, the planet orbiting around, because it's too hot for rocks there, the rocks can evaporate and form an atmosphere. But is there an atmosphere on that planet?
Okay, so this is a real star system, 1188753. This, of course, is an artist's rendition, but it is the original Tatooine planet, right, from Star Wars, the two stars and so on. So there is a temperature issue, as you point out, that tends to cause outgassing from the planetary surface. However, it's highly likely that that outgassing would have been stripped away by the planet's temperature proximity to their parent stars a long time ago. So finding an atmosphere on this particular planet, to the best of my knowledge, it hasn't been detected yet. But unless the atmosphere is really big, it's very hard for us to detect at this distance. But in this particular star's case, the planet that is in fact orbiting it, I believe, has not had an atmospheric detection. Sorry.
Can you comment on detection of moons around planets?
There's been a number of differing techniques that have been explored over the last, probably now 10 years. Because planets, of course, move around their parent stars literally as regular as clockwork, then you can make very exact predictions as to when a planet's transit will occur. And they realized many years ago that if you've got a substantial entourage of satellites around the planet, or at least a few big satellites, say for example like the Galilean satellites around Jupiter, then depending upon their orbital configuration at a given moment in time, because they and their planet have got a barycenter, a center of mass, then the prediction that we make for when the planet begins to transit the star may be off, as in too slow, later, or earlier, depending upon the distribution of matter from the satellites around the planet. And so measuring the deviation in transit time from predicted times gives us a handle on exoplanetary exomoon masses. It's a delicate observation, and it only gives you a ballpark figure. Some other observations that are being made, obviously if an exomoon is highly exaggerated, if there's your exoplanet and here's the exomoon and you're sliding across the star, then you're going to cover up a little bit more light than if that exomoon is behind or in front of the exoplanet as it slides across. And so looking for variation in the photometric signature of the light curve, courtesy of these exomoons now being silhouetted and blocking a little bit of extra, is also occurring. So those are the two primary techniques that I'm aware of, but the measurements that are being made are they're right on the detection threshold, so as to speak. So there's not a great deal of confidence in them at the moment. The timing one, yes. The exomoon sort of photometry, well, until you know what the heck the orbital period is, you never really know whether or not it's going to be in the right configuration or not. But there is certainly an expectation. Just like we've got lots of satellites. I mean, there's over 200 satellites in our solar system orbiting 8 planets, some of them very big. We believe that exoplanets around other stars will have the same types of exomoon characteristics. But detecting them, we're trying, but it's tough.
Do you think we'll be able to look further than a couple of hundred light years, or at some point?
Oh, absolutely. I mean, Kepler was able to see out many thousands of light years, but it had like nearly a 1 meter class telescope that was doing it. TESS very deliberately was given relatively modest apertures so that we would be able to just concentrate on the bright stars. I mean, I won't say it was a budget mission, but it had the deliberate intention of only looking at bright stars which are relatively nearby to us. So you build bigger telescopes or bigger optical systems into your satellites and you will be able to see much further. And as I say, Kepler was able to see thousands of kilometers, thousands of light years into the plane of the Milky Way galaxy. TESS very deliberately was limited in its capabilities in that regard. But it's still going to have thousands and thousands, thousands of exoplanetary candidates that it's going to find around its roughly 200,000 stars that it will be monitoring. And the distribution is across the entire sky, which is also very important. That it helps our statistics. Kepler was a little bit biased, although we don't think it really makes any difference. TESS is going to reassure us that, in fact, the distribution of exoplanets is quite uniform across the entire Milky Way.
From online, is it possible to detect an exoplanet's atmosphere if it doesn't transit its host star from our point of view?
With our technology, I think the answer is no. People are getting very good, though, at doing things, and you don't always hear about it too quickly. But at the moment, the only way that I am aware of that we are able to make those significant observations of planetary atmospheres is utilizing the parent star. So I think the answer is, at the moment, yeah, we've got to use the star as the light source for our planetary atmosphere detections.
A personal question. Another one, sorry. You mentioned earlier that one of the ways that we monitor whether an exoplanet goes around a star is based on the dimming of the light. And then as of late, there's been a lot of talk about Betelgeuse possibly dimming
You're going to have to pay your Christmas visa bill. I'm sorry, okay? There is no end of the road this year happening. Sorry.
But what I was going to ask was that if there were exoplanets around Betelgeuse and you were standing on the surface of one of those, and you're considering the dimming of Betelgeuse, what would be going through your mind right now?
Okay, so remember Betelgeuse is a really large super red giant. Its diameter is approximately the diameter of our asteroid belt, okay, so it's really, really very big. If you were on an exoplanet that was orbiting around it, the change in intensity of the flux of the radiation would be easily a factor of 2 to 3, so it would be a very significant change to the local environment on your particular planet. Whether or not it'd be catastrophic, it probably would be. I mean, if you changed the amount of energy that we receive here on Earth by a factor of 2 on a time scale that's measured in tens of days to hundreds of days, I doubt our ecosystem would be able to survive that. So yeah, this is a pretty titanic change. Remember, this is, as I said, a red supergiant. It's in the last stages of its life, where last stages, just to underscore this, is sometime in the next 100,000 years. That's very quick in astronomy terms. It's going to blow. It is going to go supernova, but sometime in the next 100,000 years, and we can't be any more definitive than that. But on time scales of about 400 days, it goes through a magnitude and change intensity variation from when we're looking at it in the night sky. Normally it's around about magnitude 0. It's down around about magnitude 1.2 at this point. It would be nice, wouldn't it? Yes. Yep.
Could a planet outside of the habitable zone on the cold side still be warm enough for liquid water if it had a thick enough atmosphere?
Yes. Short answer, yes. And that's one of the other complications. When we talk about planets, there are so many different variables that are out there. If your atmosphere really is thick and you are still tidally locked, there's probably enough transportation, heat transportation through winds that will move you from lots of heat this side to a reasonable amount of heat over here. There's often a lot of speculation that along the terminator, the night dark side, the temperature there would be really quite moderate, so as to speak, but it's a relatively thin sort of angular region on the planet. But yes, we are of that view. It's all a function of the atmospheric thickness. Yeah, hi.
So what role does Canada play in the exoplanet field?
Oh, that one I can answer without getting into trouble. There are lots and lots of exoplanetary centers. TEPS, what does TEPS stand for? Exoplanetary. Anyway, yes, there are groups scattered across Canada. There is a center of excellence that is located at McGill University and York University that has brought together researchers that are exclusively looking at planetary atmosphere dynamics. They are searching with a variety of colleagues in dark locations for new exoplanets. I won't say we're leading the world by any stretch of the imagination, but there is certainly significant contributions from Canadian researchers all across this country. I'm not aware of any dedicated telescopes in this country that are searching for exoplanets, but in terms of doing photometric exoplanetary follow-up, lots and lots of telescopes are doing that. But I don't know of any that are actually searching on Canadian soil. But the researchers are part of collaborative efforts that are located down both in Arizona as well as in Chile and over in Hawaii doing exoplanetary research and searches.
Hello, Professor.
Hi.
Thank you for the talk. And my question is, from the techniques that you described earlier, can we detect the direction of the orbit from the exoplanet?
Yes. Yeah. When you have a star that is blue shifting, you know where the planet is. It's, if you could see it, it will be doing a redshift. So think of the star and the planet connected by a big rod, okay? As they are moving around their common center of mass, by looking at what direction the star is doing its Doppler shifting, red and blue, you can infer the direction of the planetary orbit. Remember as well that if you've got a planetary collection, like we've got 8 planets in our solar system, all of them are tugging on our sun. So it's a non-trivial exercise to separate out all of the individual signals from each of the planetary orbits that are coming together in a combination to represent the star's motion. So, the star, when it's just one planet, it's really obvious what's going on. But when you've got 8 planets or whatever, then it becomes a much more complicated signal to receive. And so I might have sounded as if to say, the radial velocity lines are swaying backwards and forwards nice and smoothly. But when you've got multiple signals, that swaying is now a stutter and a stutter and and you're sitting there going, what? And that's where you have to introduce something called Fourier analysis. You try to extract from there the strongest signal, which is going to be associated with the most massive planet with the fastest orbital period. You extract that out mathematically. That simplifies the information. You now look for the next strongest signal. You extract that one, and slowly you decompose the signal, and you can eventually detect all of the planet's signatures as they're all tugging on the star. But now you're talking about needing really good signal strength, and sometimes that's really hard to pick up. So it is quite easy to pull out the strong signal and a lot of the characteristics about that planet, but by the time you introduce the multiple planets in a star system, it becomes increasingly complex, but doable.
Yes, so what would the maximum size of an exoplanet be, like before? So it could be a brown dwarf or something like that.
Depends who you talk to. The number is somewhere between 12 and 25 Jupiter masses. Most researchers are now on the low end of that scale. So where we move from planet into brown dwarf is as much a theoretical discussion as anything else, and that depends very much on the dynamics. Does the brown dwarf begin to fuse deuterium, for example? Is that how we're going to define a brown dwarf versus a large exoplanet? If it's got enough mass to fuse deuterium, then yeah, it's definitely a brown dwarf, okay? But if it's got that sort of mass, but there's not enough deuterium to fuse, is it a brown dwarf or is it so definitions are tough, but the answer is somewhere between 12 and 24 times Jupiter's mass. Certainly if you've got a 10 Jovian mass object, it's definitely going to be classified as an exoplanet or a planet, but once you get beyond 12 times the mass of Jupiter, it's a bit of a gray area. But once you get beyond 25, there's no doubt that is definitely brown dwarf territory.
Great talk, of course. My question is, in your understanding, when do you think, how hundreds and maybe years later, we can actually go to one of these planets to inhabit it?
Okay, so I like science fiction too. I mean, there are projects out there. I mean, Project Breakthrough, the Starship project, which wants to launch little nanochip satellites off to nearby planetary systems, hopefully in yours and I's lifetime, but it's a nanochip. You and I are not going to fit in there. There are projects called the Century Starship, which are really big arcs for 1,000 people, but the estimates to actually launch that are sort of like the GNP of Canada. I mean, there's significant cost involved. Do we have the technology? Yeah, maybe, but I think we're really still a long way from being able to mount an expedition of any size to another planetary system. I mean, we know Proxima Centauri has a planet. So we now go back to Lost in Space. Everybody remember Lost in Space? But even 4 1/3 light years away at our current technology and the speeds that we can develop, we're talking a generation ship needed. We just cannot get to enough speed for a sized vehicle that would have enough resources, and so it's a difficult project. Lots of people are looking at it. There's lots of papers that are coming out. There are conferences around the world every year that talk about it, but it's steeped in speculation, and as I said, it's very expensive. I don't think you and I are going to see it as much as I would love it. I do think we're probably talking 22nd century type stuff to be able to do that realistically, even if we had a lot of Elon Musks out there. Sir.
So I have another question. There was a recording found from Sagittarius constellation, and many think it was an alien message sent to Earth. Do you think it came from an exoplanet?
There have certainly been a lot of signals picked up by the various searches. The search for extraterrestrial intelligence, radio telescopes on Earth, have been listening for signals now for, roughly speaking, 50 years. Most of them have been traced to terrestrial signals. That is to say, if we find something which is particularly strong and a little bit unusual, we certainly spend a lot of time trying to figure out whether or not it is ET or not. To the best of my knowledge, all candidate signals that we've picked up which could have come from an extraterrestrial have had either a human cause associated with them or are associated with a natural signal. If we are listening to an extraterrestrial, you can bet it will be from an exoplanet. It is, I would think, extremely unlikely that any civilization would have an asset like a radio telescope that was orbiting around their planet or orbiting around their parent star that was powerful enough to send a signal to Earth. It's more likely that you would power such a signal from the ground. So I would say that any ET signal we do detect will be from an exoplanetary surface, but at the moment, to the best of my knowledge, we have not received a signal that we would be confident in saying it really is from ET. But we look continuously and we're looking harder, and as you saw on one of my slides, every time we find a planet in the habitable zone, we sweep that area with our radio telescopes to see if there are any signals that are either leaking out or are being deliberately sent towards us. But figuring out what that frequency will be, that's really hard.
Any other questions?
Good.
Okay, well. I think not only the lecture, but also the answers to the questions really points out why Paul deserves all those recognitions for his contributions to education and outreach. So thank you once again, Paul, for a really interesting talk and for some, another January in the books and some really very well answered questions as well. So thanks again. Okay, so the next thing on our agenda is to take a look at the announcements, and it'll just take me a moment to Okay, so let's take a look at the announcements for the next few weeks. So, our next meeting is a recreational astronomy night. This is the other type of meeting that we have, where we've got a series of short presentations from individual members. So here's the agenda. We have Arnold Brody, who's going to be presenting the sky this month. Art Ashnath comes back to talk about predicting exoplanetary atmospheres using machine learning, the Ariel telescope simulation. For some of you who don't know Artash, he's in grade 8, and he is one of the bright lights when it comes to youth in science. And he's gaining a national and international reputation, along with his little sister and his father, for doing these very innovative presentations and projects. So this will be really interesting to see what he's come up with this time. We also have Frank Dempsey coming in to talk about his stargazing travels in New Mexico. And Paul Markov tells me that he's got one more 15-minute slot available for that meeting. So if anybody is interested, please contact Paul about that, and that would give us a full slate for that night. In 4 weeks' time, on the 12th of February, we have another lecture meeting, and we have the world-renowned To Be Announced giving the talk. Yeah, we should have a speaker committed fairly shortly, but early January is not a good time to get people to commit. So we'll see what happens, but we should have an update by the next meeting. Okay. Our regular observing sessions, the public solar observing at the Science Center. The next session is on Saturday, the 1st of February, out on the telescape from 10 until noon. And in the usual way, we'll have people to meet and greet and bring people over to the telescopes. And that will go on if the sky is clear. So Sean has the unenviable task of deciding either late Friday or very first thing Saturday, whether or not it's a go. So if you are interested in helping out, please take a look at our website or on our social media or the forum to see whether or not the event is a go for that day. Towards the end of the month, we have other things going on. Next week, we have the Dark Sky Star Party on the first clear night of the week. I'm not sure whether we're even going to get a clear night. If we do, it's going to be awfully cold. So anyway, Adrian, I guess you're going to be making the call on these? Yeah, okay. So at Long Sault Conservation Area in the parking lot, first clear night of the 20th to the 23rd, that's next week. We'll have the Dark Sky Party, and then the City Star Party the following week on the first clear night at Bayview Village Park. And again, the same venues, the forum, the website, and our social media. We're also doing some outreach, and the first outreach event is going to be an interesting one. We had a very, very long association with the Royal Ontario Museum from 1968 until the planetarium closed in the mid-90s, and we're starting to work with them again. And on Friday the 24th, they have their first ROM After Dark programs. So this is a special program on Friday evenings throughout the year. And this time they've decided to have an astronomical theme looking at the moon. The national office's Jenna Hines is going to be down there that night doing a presentation, and she asks if we can help with providing some telescopes. And if you contact Ian Wheelband through the public education at RASC-TO.ca, he can give you details on what you need to do to get your telescope down there, et cetera, et cetera. But it is a unique event at the ROM. We also have an outreach event here going on the 1st of February in the evening. the second of our stargazing evenings on Saturday nights at the Science Center. And during the winter months, we have this special 2-hour slot just as the Science Center is closing up to give the visitors a last bit of science before they head home. And again, we can use some help with people bringing telescopes to set up just outside the entrance to the Science Center in the evening. And again, this is weather dependent, and so again, we will have a go or no-go call in the usual way. And Tom, I think you're handling that. So again, if you would like details on what that program involves, please talk to Tom about that. Okay, a lot of our work depends on volunteers helping out, and Blake Nancaro is our volunteer coordinator who can provide all sorts of information and guidance and can match you up between your interests and what we need to do. And so again, if you are interested in helping out and haven't already, please contact volunteer@rascto.ca to discuss what you can do and what we can do to help you with volunteering with our work. One of the features of membership for those of you who are new to the organization is that we have our own dark sky observatory just west of Collingwood on the west side of Blue Mountain. And the property there has a 3-bedroom house, fully furnished and outfitted. And we have 3 observatory structures there. One which contains this lovely 16-inch Recce-Chrétien telescope that you can use on supervised nights. During the winter, we don't have supervisors on board. However, we do have the Sue Laura Observatory, which is our imaging observatory there that's available for your use, and so you can book rooms and go up there. The only thing is that, particularly with the snow that's expected tonight as well as over the weekend, we figure that's really going to shut the road down now. And so there is a special winter parking arrangement. You park at the top of the hill next to the observatory property, and there's about a probably 1/2 to 3/4 kilometer hike down the hill to get to the place. And you do have to bring in your food and so on. But again, the place is available for your use throughout the year, and you can reserve online for space there anytime. The property also has a number of rented out spaces, a slab which has power and internet connections, and we also have on these locations sky shed pods that people can use to house their own equipment. One of these is coming up now for sale, and so Blake Nancaro is helping the owner to sell this thing. And if you do have any interest in that, please contact Blake to get further information about either the pod itself or the entire site, because the site is owned by the center and we rent it out to the owners, and the pod itself is a structure that sort of changes ownership with time. Okay, another feature, again for the new members, is our telescope loan program, where you can at no charge borrow telescopes of various types. And we have quite a few, including a full astro imaging setup. And so do we have any of our telescope managers here? There's Mark right there, who is one of the 3 current telescope loan managers, and he can give you further information about that. Okay, and finally, the meeting after the meeting. There are quite a few people who will be repairing to the Granite Brew Pub at Mount Pleasant and Eglinton for a quick bite to eat and a drink. After the meeting, you're welcome to join us there. Also, Sean has just reminded me, for those who are in the room, that we still do have some observers calendars for 2020 available, and they are $15 each, cash only. And again, I don't know how many we have, but about 10. So they're still available, and you still have a good part of January to use. So there we go. All right, so that's it for this time, and we will see you in a couple of weeks for the recreational astronomy night. Have a safe trip home, and we'll see you next time.